So welcome back, everybody. The topic this week is an explicit derivation of one very popular approximation to copper cluster theory, which is called simply copper cluster doubles. And this is something which also links well with the second midterm. I mean, in the second midterm, you are not asked to implement copper cluster theory because we haven't finished the lectures before now. And then it would be way too late to include that in a midterm. But if you want to, in the final oral examination, you could take the programs which we have here, which is an implementation of copper cluster doubles, and you could compare that with what you get from many-body perturbation theory and full diagonalization. And since copper cluster theory is also an approximation to the full many-body problem, then you can compare approximations like Hartree-Fock, many-body perturbation theory, and copper cluster theory. And at the end of the slides this week, there is a program which implements this copper cluster approximation. And these are the elements which I want to discuss with you today. I may bring in some of the elements tomorrow, so I haven't made up my mind whether we are going to have a full lecture tomorrow or whether we focus more on the midterm. So this is very much up to you guys as well, because we could actually sit down then, like we did last time. In the previous midterm, we used the whole Friday to discuss the midterm. And then people could come and go as they wanted. So let's just see how things evolve then, right? Then, if you scroll down the slides here, at the very end, you will find there are some repetitions here, some questions actually, which also link with a second midterm. One of them is actually a question about Hartree-Fock theory. And many of you have probably looked at Hartree-Fock already. And you probably realize that after you put up the equations, there is nothing to be done, because you already are on a Hartree-Fock basis. So it means that when you revisit things, you will see many things which are known. So one of the things which I actually wanted to start today with is to remind you of a cumbersome and not very efficient way of setting up the FCI equations. So I'm actually going to start with a reminder of the exponential ansatz as a way to approximate the exact wave function. And then with that, we are going to compare with an approximation which is going to be copper cluster with only two particle, two hole excitations. Then we are going to compare that with the type of truncations we can make when we rewrite the full diagonalization problem in a kind of clumsy way. Because then you will see the link between an exact diagonalization and the approximation which copper cluster theory entails. And at the very, very end here, and this is more relevant if you want to include that in the final presentation, you could then, in addition to the results you're getting in the second midterm, you could then actually just use and run the code here. So concerning the midterm, you will also notice that there is a comparison with exact diagonalization here. And if you just read, you will see that this exact diagonalization here actually shows you how your Hamiltonian matrix should look like. Okay, so you have a kind of answer to one of the problems. I hope you don't get offended if I do that. And then the program here is something which we will discuss in more detail when we've gone through the equations. Okay, so what I wanted to do now is to first remind you quickly about the basic copper cluster equations which we're going to set up. But then before we derive the final equations, we are going to look at as I said, the cumbersome and clumsy way of actually rewriting the full configuration interaction theory problem. Okay, so that's roughly the scene for the day. And then we'll see how far we get. And I may sneak in a lecture in the first hour tomorrow. And then we spend the rest of the time discussing the midterm. Okay, so I'm going to switch now back to the whiteboard, and we are going to essentially stay there for the rest of the day. So let me remind you of the exponential ansatz quickly. So let's just spend some few minutes on that. So what we have done till now is to look at many-body perturbation theory and FCI. Now, today we are going to look a little bit closer again at what we did in the beginning of October, actually end of September, when we wrote out the FCI equations. So in the FCI case, if we now focus only on the ground state, then we have the Hamiltonian acting on psi zero, and we are now just focusing on the ground state. But this is a problem which is generic, so we can have any state if we want. And then we know that this wave function psi zero is a function which we could write out when we use intermediate normalization in terms of a correlation operator, which then brings in the admixture from all the other Slater determinants which we have. So this is then acting on the unperturbed Slater determinant, or the non-interacting one. And the non-interacting one is actually an eigenbasis for the non-interacting Hamiltonian. And typically these phi zeros are Slater determinants. And then, as you may remember, we defined the correlation energy as the difference between the exact one minus the expectation value of the non-interacting Hamiltonian plus the interaction. So this is what we call the reference energy. But let me quickly remind you of these terms. So the E0 ref is the same as phi zero, this ansatz which we have chosen for the ground state. Okay, so this is just a quick reminder. And then I also remind you of this operator, where we now have this one written in terms of an admixture of particle hole excitations. And we are setting larger than zero because zero particle, zero hole is the ground state ansatz. And this is now given by these coefficients of P, and then we have this operator H of AP of phi zero. And this H of AP is an operator which then contains a string of creation and annihilation operators. So this could be a dot, 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 and then we have an AJ and AI here. So depending on how many particles and holes we have, this would just be a string of creation and annihilation operators. So this was essentially what we did for the FCI calculation. Now, this wave function which we have, the psi zero, is equivalent with what we called for the exponential ansatz. And we proved that for a general operator of this type, which we have here, that when we have this type of operator, then we could actually rewrite then Thouless theorem for the one particle, one hole excitation is already an example for that. But we could actually rewrite psi zero in terms of what we call the exponential ansatz. And then we have this operator T acting on phi zero. And this operator T is an operator now which contains one particle, one hole excitations. We have two particle, two hole, etc., up to n particle, n hole excitations. Now, if we include the full set of excitations, we're actually setting up the full problem. And this is not what we want, because we want to use this as a way to truncate the problem. And as a quick reminder, this T1, it was simply a sum over the hole and particle states. And then we have an AI, and this is then acting on the ground states. But this is now an operator. And then this is multiplied with an amplitude. So these are the unknown amplitudes, which we are going to find a set of nonlinear equations, which we're going to use to solve this problem. And then we have the T2 operator, which is an anti-symmetrized operator. This now acts on two particles, and it has a matrix element or an amplitude, which is also anti-symmetric under the interchange of I and J and A and B. And then we have A. So if we now write this out in this particular way, you can also see why we have this ordering, which we have seen many, many times. So this is a two-particle, two-hole excitation. And if you look at this term here, then we know that when we use the anti-commutation rules, I can interchange now B and I. So I get a minus sign. But this is then the same. This is the same as AA, AB. I get a minus sign, and then I swap again AJ and AI. So this becomes equal to that. So what we have then is a one particle, one hole squared. So this is a two particle, two hole excitation. So this is the two particle, two hole. This is again the one particle, one hole. And then we can continue like this. Now the typical problem which we ended up with then when we are setting up the diagonalization problem is the following one. So what we have is now that psi 0 is given by this E of t to some approximation acting on phi 0. So that means that when I act with the Hamiltonian, what I'm having now is E times t of phi 0. And then clearly this should now be given by the eigenvalue. So this should be given by E0 of E of t of phi 0. So what is pretty common to do then is to multiply this with e to the minus t. And when we multiply this with e to the minus t, then we have the standard couple cluster type of operator, which we are going to look at. So if you multiply this with e to the minus t of e of t here of phi 0, let me quickly remind you of this. This is again the same as E0 multiplied with phi 0. And then it's very common to replace this h with the normal ordered operator plus the reference energy, like that. Then, if we now reshuffle a little bit the equations here, we remember now that the correlation energy, which is a difference between the exact ground state energy and the reference energy. So if we pull this term here over to the other side, then you see that this is just a constant. So that means that we have a constant in here. And then we have e to the minus t times e to the t. And what we end up with then is that we have e minus t times this normal ordered Hamiltonian times e of t multiplied with phi 0 is equal to delta e 0 multiplied with phi 0. So what we call this guy here is actually a similarity transformation. It could be a unitary transformation, but this is a transformed Hamiltonian. And remember now that this h of n then was given by the one body term. And now today we are going to look at these terms more explicitly. So this is just a one body. And I'm going to remind you of these a little bit later. And this is the two body term. And we will essentially stay with a Hamiltonian which contains at most two body terms. So this is the operational equation, which we are going to look at in more detail after this lecture. In this lecture here, we're actually going to simplify this t to just t2. But let's try to stay a little bit general first, because now I wanted to go back and link to the standard FCI calculations. So let's take a step back and rewind our semester back to middle of September, end of September. So 2 months ahead, 2 months back. I hope that's not too much to ask for. So let's look back at FCI. And now we're going to look at this more clumsy way of setting up the FCI equations at FCI. So what we had with FCI, so we have the Hamiltonian then acting on the exact wave function, and this is now equal to E0, the exact energy of psi 0. Now, this is nothing. When we now look at the equations, it's the Hamiltonian acting on this chain of Slater determinants. And now I'm going to set up all the determinants which we have. So we have this pH, and then we have these coefficients CH of P. And now I'm just going to put in all the creation and annihilation operators in the state phi H of P, which is now given by this chain of creation and annihilation operators acting on the reference vacuum state. So let's just put this in a parenthesis, and this is obviously equal to E0 multiplied with the sum of pH, CH of P, of phi of HP. Now, what we did when we looked at many-body perturbation, FCI calculations, what we did then, in order to set up the rows, so if you go back to the matrix which we put up, so we would have now matrix elements, the Hamiltonian matrix. So we would have something which we call H00, H01, which is the one particle, one hole case, and then we have H0, and this is 0 n particle, n hole. And then we have the coefficients here where we had a C0, C1, one particle, one hole, etc., all the way down. And then we have H01, so this is the overlap. This, if we now just look at this specific one, this is the overlap between the ground state and the first one particle, or the block of one particle, one hole states. And all the way down here to H of 0, n particle, n hole. And then we have the final matrix elements where we have n particle, n hole states and n particle, n hole states. So in principle, we have an infinity of such states, but we will obviously always truncate. So that means that the matrix becomes finite dimensional. But these blocks, which you see here, can be pretty large. Now, what we did then, in order to get this equation, when we write it out, so we are simply multiplying these elements with these coefficients. So if we take every row here, and then think of what we have done in order to get these elements, we actually, in the first one, we are multiplying with phi 0. In the next one, we are multiplying with a particle hole state. Then we have in the next one, we have a 2 particle, 2 hole, 3 particle, 3 hole, etc. So this is essentially the way we found all these different matrix elements here. So what we are having is a matrix being multiplied by a vector. Okay. So let's bring back row by row, but we are going to stop at the second row only here, no, the third row, which involves a 2 particle, 2 hole. So let's do that. So we take this equation, which you have here now, this equation and that one, and we multiply from the left with phi 0, okay? And you will see that later I'm going to repeat the same thing if we go back to copper cluster theory. So if you now look at this equation here, this equation which you see here, this is the equation which is in principle equivalent to this equation. So they represent the same if we can run the exponential here to all orders. That means to all particle hole excitations which are possible. So these are equivalents. So what we are going to do now in order to find equations which we can solve, we will also do the same thing here. After we've done the FCI, we're going to multiply with phi 0. We are going to multiply with phi I of A, and we are going to perform the same multiplication with phi ij AB. And then you can continue along these lines. Now, I promised you a kind of boring and exercise which is not convenient from a computational point of view, because you end up with a set of nonlinear equations for the unknown coefficients CHP. Does that sound okay? Any questions so far? So let's write this out. So we are now multiplying phi 0, and we are taking the first row in the matrix, and we are multiplying that with H, and then we have the set of particle hole states, CHP and phi HP, like that. And this is something we want to put equal to phi 0, and then it's multiplied with E0, and then we have the sum over these particle hole guys, CHP, multiplied with phi HP here. We did this actually back in September, but I'm going to repeat it essentially because we want to link with couple cluster theory. Now, the other thing which we introduced was this intermediate normalization. So what we did then was to set the coefficients with 0 holes and 0 particles. We just put that one to 1. That means simply that we reshuffle strength on the coefficients to all the other terms. This is just called intermediate normalization. And then we know that the basis which we have chosen is an orthogonal basis. So when I take the overlap between this state and states which are different from it, it has to be 0. So what I get then, when I write this out, I get a phi 0. Let's just write it out. I have a phi 0, and then I have my H, and then I'm going to have phi 0 plus, and now I'm going to have the sum over the particle hole states. So this is the one particle, one hole guys. And then I have my phi 0. And this is then something which acts on this state, phi IA. And then I'm going to get a B, I, J. I have the coefficients from diagonalization. So in principle, what I'm doing now is pretty stupid because when I diagonalize, I get the energies and I get the coefficients. So I'm doing something which is not so meaningful, but I'm going to show you a way you can solve the same equations, which results in a set of coupled nonlinear equations in the unknown coefficients. And then we would have H times phi I J A B. And this actually terminates here because we have assumed that we have at most a two-body interaction. So if I have then a free particle free hole state and I have only a two-particle interaction, then due to the Condon-Slater rules, that overlap is going to be equal to 0. So with a two-body interaction, this sequence, which in principle should run to n-particle n-hole excitations, if you spool back in time and look at the exercise you did in the third or the fourth week on the Condon-Slater rules, then this is a consequence of that. So this terminates here. And if we then look at this, this is nothing but, and this is going to be equal to E0. And this is nothing but the E0 ref, which we get from the first term. And what we have next is an AI, and then we have CIA. And in this particular case, what we end up with is a interaction element, which is given by this operator F, which I'm not going to redefine, plus the AB IJ and CIJ AB. And this gives us a integral over the two-body interaction, which is also anti-symmetrized, and this is equal to E0. Now, if we did a Hartree-Fock calculation, with a Hartree-Fock calculation, then this integral here is exactly equal to 0. So if we are using a Hartree-Fock basis, then the only term which survives is this one. So if I now shuffle this to the other side, what I'm going to get is actually delta E, 0, which is now E0 minus E0 ref. and that is exactly equal to the sum over one particle, one hole states, CIA, and then we have the state I, F, and A, plus this integral over the two-body interactions, Cij, AB, and then we have AB, Vij. And I'm going to skip this anti-symmetrization sign because we are going to assume that this is always anti-symmetrized. So this is an exact equation. And when you diagonalize, you have these coefficients. So there's nothing to be done. Now, one of the things which we did last week and the week before in many-body perturbation theory is to show that we could actually construct, by perturbation theory, these terms order by order by looking at the wave operator. This is also one of the exercises which you have in the second midterm, where you compare these terms which you get from exact diagonalization with the wave operator to first order. So this is the easy term. Let's now go back here and look at what happens when we take this equation here and multiply with phi IA, and the next one, which is phi ij AB. Okay? Because that would be the next row and the next row here. So what we get then, if we now go back, I'm going to do this in a somewhat boring way. So what we have now is phi IA. And if we look back at the equation which we had, so this is the equation we are starting with. So we are simply performing these multiplications. So we are taking the Hamiltonian, H, and then we have the sum of a particle hole, including the ground state excitation. The ground state, sorry, not excitation, but the ground state ansatz. Like that. And this is equal to the term phi of IA. And then we have E0. And then we end up with the term here, which is simply a sum over PH. And then we have a CH of P of phi H of P. So if you look at the last term, since all the states here actually built on an orthogonal and normalized basis, it means that when it picks phi 0 here, that has to be 0. This is just a constant. So the only term which survives here is actually the one which involves phi IA. So the left-hand side is actually pretty easy. So I'm going to get E0. And then what I'm going to have then is E0 multiplied with CIA. That's the only term which survives here. Then I'm going to write out the other terms. And what we have then is obviously a whole chain of terms here which are going to come in. So let's do that. So we will have a phi of IA. We have the Hamiltonian, and then this is going to act on phi 0. That's the first term. And then I get a new term here where I have a Bj, and then I have a coefficient Cjb, and then I'm getting elements of the type H, and this is multiplied with phi jb, like that. That's the next one. And then I have a new one, which is BC and JK, CJK, BC. And then I have this state, phi IA of H. And then I get my phi of J, K, and BC. That's the next term. And plus, so this is equal to, and then I have a free body term, because now I can connect a one particle, one hole to a free particle, free hole term. So there will be a BCD, JKL, and there's going to be a new coefficient, JKL, and then BCD. And again, I'm going to have a phi of IA, and then I'm going to have this overlap here. And that's the last term, because I have a two-body interaction only, and I cannot connect a one particle, one hole excitation to a four particle, four hole. So what you see now is a kind of pattern here, that these number of terms which you have here this keeps to increase. And you see now that the coefficients which you have, unless you have diagonalized, this coefficient is unknown, this is unknown, and this is unknown. Keep also in mind now that when you look at the equations, if we go back to the equation which we had here, you see now that the energy which we have defined, E0, here, is actually given in terms of these amplitudes which you see here. So that means that when I now plug in this equation, when I now plug in E0 here, then there's going to be a term which looks like this, plus the reference energy, obviously, right? But if you look at this E0 term plus E0 ref, you see now that you have the coefficient CIA here, but it appears here also. So this is where you have the nonlinearity in the unknown coefficients. So the typical way you would solve these set of coupled equations for the unknown coefficients is that you would start with a guess for these coefficients, and then you start iterating. And typically then you would use a root finding method like Newton's method to find the roots of the equations, because you're just putting, when you shuffle these terms to the other side, then if I shuffle this to the other side of the equation here, I will have 0. So I'm just going to find the roots of an equation which involves all these coefficients. So that's essentially what you're doing. You're rewriting in a clumsy way something which you can get by an easier method, which is diagonalization. Now, the reason why I'm doing this is that this links immediately with what we are doing with copper cluster theory, so that you can see how the equations actually come through. So this doesn't look very nice, because we need now, as I said, when you look at the equations here, if I'm plugging in the equation for E0, I'm getting something which is nonlinear in this term here. When I now go to the next equation, which means the next row here, the one where I multiply with phi ij ab to get this third row, then you will see that there will be a coefficient which is going to be Cij ab on the right-hand side. So let's see that. So what we're doing now is to take the next one, next step. So I'm just going to leave this as it stands. I'm not going to write it out. But I want to set up the equations because we have already calculated these overlaps, or these transition probabilities, as we might call them, or expectation values, when you have the same state on the Brownian-Ketz side. So this is something which we have already evaluated. And using the Condon-Slater rules, you can actually set up the analytical expressions for these. And then you have to look up the integrals. So everything you see here, here, and here can be calculated. You see the basic recipe which we are, by which we can rephrase the diagonalization problem. So the next step which we are going to do now is simply to multiply with phi ij, and you see that this can be continued up to n particle n holes. So that means that you will have up to n particle n hole rows with equations which involve the coefficients, the unknown coefficients, as nonlinear equations. You would not like to solve this equation fully, because that's essentially a waste of CPU cycles. So in this case now, we would now have pH, and then we have again CHP multiplied with phi HP, and this is obviously going to be equal. When we now set up the states, I'm going to get this one to simply be equal to Cij AB. So in the previous case, I had a 1 particle, 1 hole state, and now I'm getting a 2 particle, 2 hole coefficient. And if I write out the first term here, what I get now is that I get phi ij AB, and then I have my H, and now I have my phi 0. And then I have plus, and now I get my sum over C and K. I have a coefficient C, K, C. And then I'm getting overlap between a two-particle, two-hole state. And I'm just going to put a multiplication sign here of phi of Kc. Then I get a new term, which is an ABIJ. No, sorry, not, I should avoid those symbols. It's actually a CDKL. And then I have the unknown coefficients, CKL, CD. And then I have my phi, IJ, AB, A and B of H. And then I have my phi of KL of CD. And then I'm get more laborious because then I have a CDE. I get a three-particle free-hole term, and this is KLN. And then I get a CKLN, a CD, no, not CD. This is a letter E. It looks like an L, but it's actually a letter E. And then I have a phi, IJ, AB of H, and then I have my phi of KLM and CDE. And the final one is actually a four-particle, four-hole because I have a two-body interaction. And I can link a two-particle, two-hole state with a four-particle, four-hole state. If I had a three-body interaction, I would actually have been able to link with a five-particle, five-hole states. And you see, this is not exciting. Eh? So when you've done this sometimes, you don't want to repeat it. So C, K, L, M, N, and C, D, E, F. And I'm just going to put dots here because you see what it should look like. So that stops there. Now, there's nothing which hinders you to set up a similar equation for three particle, three holes, etc., etc. Because then what we have been doing here is simply to rewrite the expressions which we get when we multiply this row with that one, this row with a vector, etc., etc. That's basically what we have done now. Okay? So let's go back to copper cluster theory and let's see how this can represent an approximation to what we are doing. So you can see that when I set in the expression for the energy into here, then obviously this leads now to a nonlinear equation because I have the energy here. I will have a nonlinear equation of these ones, but I also am multiplying with these coefficients. So this becomes a set of coupled nonlinear equations. Now, the copper cluster approximation is also going to give us a set of coupled nonlinear equations, but they will be truncated. And they will be truncated so that we can sum correlations to infinite order in a systematic way. So the nice thing with copper cluster theory is that it allows for systematic expansions where you can include correlations of a given type to infinite order. So I'm not going to say more about this. I just wanted to bring back the equations. Typically, if somebody asks you to solve the equations this way instead of diagonalizing, you should obviously ask that person to find something else to do instead of pestering you. But if you now would insist on that, the typical way of solving these equations is to start with a guess. And the guess, which you would typically use, is to use perturbation theory. And the equation we derived 2 weeks ago for perturbation theory, the wave operator to first order, which you're also going to use in the midterm, this is something you could start with if you want to iterate. And as I said, what you would be doing here is simply to, in these equations here, you would just bring this to the other side. Because if you look at these equations, the term which you have here, this term, is something we have already calculated. So that term here is a term which just gives us an overlap, which is just AB, V, IJ. And then we would have terms which involve two particle, two hole excitations, one particle, one hole excitations, etc., etc. So let's bring back copper cluster theory. So this CC theory. And now we're going to make a simplification. So our first encounter is to derive the equations for the T2 approximation. So now we do an approximation, and that means that the amplitude T is just equal to T2, which is 1 divided by 4, and then AB, IJ, and then I have the unknown amplitudes, Tij, AB, and this is then multiplied with A dagger, AB, AJ, AI. So that means that my ET times phi 0, which is my exact expression if I don't make any truncations in the operators T, this is now going to be represented by ET2 of phi 0. So what we are going to assume then is that T1 is equal to 0. So that means that all the T1 amplitudes, that means that all TIA are set to 0. So that's an approximation which we are going to make. That means that I'm going to have two equations only, which I'm going to set to 0. So if you now go back to the Hamiltonian we had, so we're going to have ET2, we have the Hamiltonian acting on phi 0. And then this is equal to E0. And now this is an approximation. So I'm not going to put E0 here, but I'm going to call this for CCD. So this approximation, which you see here, this one, and I'm going to mark it here, this is called copper cluster with doubles. And D is equal to doubles, which actually means two particle, two hole excitations. So I'm going to put that subscript as CCD, just to indicate that this is not the exact energy. And this is then multiplied with the true eigenstate. Oh no, the ansatz for the ground state. And sorry, I also have, I forgot here. ET2 times phi 0. So what I'm going to do now is to repeat the same exercise which I did in the FCI calculations. So I'm going to multiply with phi 0 from the left, and I'm going to multiply with phi ij AB from the left. And then I will get two equations, which I'm then going to use to find the unknown coefficients, Tij AB. So I'm not multiplying, I'm not having, so I have no phi IA, because I have simply assumed that these excitations don't exist. Okay? So this is just an approximation we make. Next week, we are going to derive the equations where we include the T1s, and that is the standard basic copper cluster approximation, which is called copper cluster with singles and doubles. So for those of you who are doing nuclear physics or quantum chemistry or been using these methods, these are common acronyms which you will encounter. And then you have perturbations of these. There are approximations to triples excitations, and people have dedicated their professional lives for decades in order to improve upon these different approximations. And people will obviously fight each other at different conferences of who has the best approximation, as humans always do, right? My method is better than your method, etc., etc. We can't escape human psychology. Even if we try to be scientists at our best, human psychology somewhere always kicks in. So since we have now excluded the one particle, one hole excitations, it means that we are only going to look at the part which deals with the phi 0 and the two particle, two hole excitations. So let's now repeat the same exercise, which we did with FCI. So with FCI, what we did then was simply to multiply from the left with either this one or that one. And now we're going to do exactly the same thing. And we're also going to keep in mind, if we look at these equations, although these are not the equations which we will use at the end, if we look at the e to the power of t2, if we then use the standard Taylor expansion, we have plus t2 plus 1 over 2 squared over 2 factorial t2 squared, etc., etc. So this is what the operator is going to look like. But let's wait with writing that one down. So the first term which we take now is simply phi 0. And then we have the Hamiltonian, and then ET2 acting on phi 0. And we know that this one is going to be equal to E0, which is just a constant, by the way. And then we have the state phi 0 multiplied with ET2 and phi 0. And then you see quickly then that on the right-hand side, there is obviously only one term which survives. And that is when we now look at the Taylor expansion, which you have here, because as soon as I have a T2, this one acting on the ground state here creates a two-particle two-hole state. And then when I take the overlap with a two-particle two-hole state with this guy, then that gives 0. So all T2s to some power higher than or equal to 1 gives 0. So that means that the left-hand side, sorry, not the left-hand side, the right-hand side is actually just E0. So that's pretty easy to isolate. If I then look at my next term, the one on the left, so what I have now, if I just write this out, I'm going to get phi 0. And then I have H, the Hamiltonian, and then this is going to act on 1 plus T2 plus 1/2 T2 squared, etc., acting on phi 0. So the first term which we have is actually the one which we have defined earlier, which is our reference energy. So this is nothing but E ref. Then I have a new term, which is going to be phi 0. And then I have my Hamiltonian, and then I have T2 and phi 0. But now there is an additional term. If we look at the next one, the next term is going to include a T2 squared. So keep in mind now that if I have a T2 squared acting on phi 0, this will in general produce a 4-particle 4-hole state. So that means that I have a 4-particle 4-hole state. When I act with this guy here on this one, then I can at most reduce that to a 2-particle 2-hole state. But then the action of this one together with that can give us the lowest type of excitation, which is a 2-particle 2-hole excitation. But then on the bra side, I have a 0-particle 0-hole. So 2-particle 2-hole overlap with the 0-particle 0-hole is 0. And the high order terms, like a T2 cubed, gives us a 6-particle 6-hole. I have a 2-body operator only, which can bring me down to a 4-particle 4-hole at most, or the lowest type of excitation. And I have to match that with a 0-particle 0-hole. So that means that here, these higher order excitations actually disappear. And the only term which remains is actually this one. And this has to be equal to E0. And now you see that, and actually this is now not E0. I should be a little bit careful because I actually put a proper name onto this one. This is ECCD. I forgot that, what I wrote before the break. CCD. So if I then shuffle this one over to the other side, what I'm going to get then is the following. So I get phi 0, and then I have the Hamiltonian. But now the Hamiltonian, because I've taken out if you now look at this term, I put this to the other side, this term here. So I'm simply left with this term. So I have a T2 of phi 0, which is equal to delta E CCD, which is now given by E CCD minus E0 ref. That can be a Hartree-Fock reference energy, or it can just be your chosen favorite basis, which you have calculated. Now, let's take a look at what we have here on the left-hand side. So now we're just going to put in the expressions for these operators, okay? So what we have, if we now look at H here, H contains now either a one-body, two-body operator. So H is equal to E0 ref plus the one-body part plus the two-body part. So E0 ref is just a constant. And we know that the first term then gives us phi 0 with T2 on phi 0 multiplied with E0 ref plus, and then I have phi 0, and then I have my Fn, one-body operator of T2 of phi 0 plus a phi 0 of V of n of T2 of phi 0. Now, if I look at the first term, this one creates a two-particle, two-hole state, which I'm trying to match with a zero-particle, zero-hole state. So this term here is actually equal to 0. Okay? That sound okay? If I look at my next term, this is a one-body operator. So I have an operator AP dagger, AQ. This is a two-body operator. So I would have A dagger, AB dagger, AJ, AI. Now what happens when this one acts on this state, I get a two-particle, two-hole state. But since this is a one-body operator, I can never bring it down to more than a one-particle, one-hole state. So the action of this one together with that one acting on this creates a one-particle, one-hole state times some constants. And then I'm taking an overlap between a one-particle, one-hole state with a zero-particle, zero-hole state. So this term here is also going to be equal to 0. So you can think of this in terms of types of states you produce. So when you look at this overlap, for this one to be different from 0, then the action of these guys here have to give this one times some constants. In our case, this creates a two-particle, two-hole, and you can see that immediately now if you do the contractions. Because if you do the contractions, so let me just show you that in case you, because I've been doing this for ages now, and I can just watch expressions and I can tell you immediately once which are 0 and not, but just watching the structure. But it takes some time, and in order to get this kind of experience, you need actually to run some calculations. So what you have now are two normal order chains of operators. And when I set the contractions, this is a set of contractions I can make with the operator, and I can also make this one. These are the non-zero type of contractions, which you get. But what happens then is that you will always have a set of operators which belong to the same chain of operators, which are left there uncontracted. So these two guys give obviously 0. And you can see that immediately because this removes a particle, this removes a state. So this will be a two-hole state which I create with the action of these two guys. Or if you look at these ones, so this contraction is equal to 0 because this is a particle state and this is a whole state. If I look at what I have here, this one and that one creates a one particle, one whole state, which I have to match with a zero particle, zero whole state. So irrespective of which one of these contractions we pick, there will always be something which will produce a state here, which is different from the final one here. So this term is going to be equal to 0, and we're only left with that term. So if I then collect everything, and we look at what we had, so we have delta ECCD, and then we have the last term. So we are getting now the following, phi 0. I have the two-body interaction. I have the T2 operator, and I have phi 0, which is equal to my delta E CCD. And now we're going to look at what we get here. So what we're going to do now is simply to set up the contractions. So this term is equal to 1 divided by 4 from the interaction, 1 divided by 4 from the T2 operator, which is an anti-symmetrized operator. I'm getting a sum over PQRS, and I have a sum over ABIJ, and then I have phi 0, and then I have the operator AP dagger, AQ, AS, AR, and then I have my two-particle two-hole excitation operator, multiplied with phi 0, and finally this is multiplied with an integral with PQ V R of S. Now, we've already done this exercise many, many times. So when we looked at the FCI calculations and we calculated the matrix elements, we did it. So I'm just going to remind you quickly of what kind of terms you will be getting. So a typical contractions which you could have would be the two states here are with this one. So this gives us a delta RA. I can have my contraction here. This gives my delta SB. And you know, as we have seen before, is that we can then interchange this with that and this one with that. Okay, so that gives us two terms. And due to the anti-symmetric integrals which we are looking at, we are going to get the same contributions. So we've done this several times. Then there is a set of contractions here, which will give us delta QJ. And then we have this one, which gives us a delta PI. So we have these four Kronecker deltas due to the contractions. And we know that we can also interchange this. So we have this one going there and that one going here. That gives us a crossing line. So in total, there are 4 contributions. So I'm not going to set up all the 4 because we did that when we did the FCI calculations, because we calculated a similar term there. Except that in the FCI case, we had a state which was explicitly defined as a two-particle two-hole excitation. So if you look at this term here, and you now go back in time to what we did before the break, then there is a term which we had in delta E0, which is this one. So that's the same term, which we are looking at now, because this is already a T2 times phi 0. And then we have the Hamiltonian here, and that was a two-particle two-hole excitation, which we got at the end. So if we now go back to what we have here, if we now put up all the contractions, what we will find, and just setting up the final result here, this is going to be the same as 1 divided by 4. By the way, I forgot actually to set up TIJ-AB, the amplitude. Sorry, that should also be there. So what I get then is AB, IJ, TIJ, AB, and then the integral due to all the Kronecker deltas, that becomes simply equal to IJ, V, AB, anti-symmetrized. And this is equal to the correlation energy from copper cluster theory. So if you think of FCI, just let me write that one back again. Then we had delta E0, the exact one, was given by a sum over AI, and then it had CIA, and then it had I of F of A, plus a sum over AB, IJ, and then it has CIJ, AB, and then I have this element IJV, AB. So if I have a Hartree-Fock basis, so this is 0 with Hartree-Fock. So if I zero that out, you see now the similarities, right? So this is what you would get from diagonalization. The only difference is that this is the exact correlation energy. This is an approximation. But they look very much the same. And the only thing I don't have now is a recipe to find these amplitudes. Okay? So that is similarity 1. If I had included the T1 in these equations, there would have been a term which looks like this one. Okay? And you will see that next week when we introduce T1 plus T2, there will be a similar term with TIA here. Any questions? So let's move on now, because now we did the first equation. This is the easiest one. And now comes the nightmare. And it's even with a T2 level, it's a boring exercise in the application of Wick's theorem. This is actually something which you can automatize if you use symbolic Python. There is actually a package which is called Wick, and that sets up the contractions you want to calculate, and it finds all the contractions for you. Because it's not a very exciting exercise, but I'm going to do it anyway. And I'm going to test now to see how many of you stay asleep. Okay, so the thing we didn't do now is actually to take the second term. So now we're going to multiply with this one the same expressions which we have here. Okay. So now we have an expression here where we have the amplitudes in terms of the energy. And when we are going to set up the equations to iterate, we are going to set up a guess for these amplitudes. And the guess is normally first order perturbation theory for the wave operator. Okay, so let's go to the exciting part here. So what we have now is the term phi ij, which we are multiplying from the left, as we did with the Hamiltonian, to obtain the Hamiltonian matrix of ET2 of phi 0. And this is going to be equal to phi ij AB, and then I have E0, and I can just write out 1 plus T2 plus T2 squared divided by 2 factorial plus 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 acting on phi 0. And if you look at the left term, no, sorry, the right-hand side, then the first term is a term which is going to match this one with that one. E0 is just a constant times 1, so that's obviously 0. Then this guy here produces a 4-particle 4-hole excitation, which I want to match with a 2-particle 2-hole. So all terms with power T2 to the power of 2 or higher are going to vanish due to the orthogonality of the states. So the only term which remains is actually this one. So the right-hand side is then going to be given by phi ij AB of T2 with phi 0 multiplied with E0. So if we write this out now, this is nothing but a state which is phi 0, and then I have my A, and this is AI, dagger, AJ, dagger, AB, AA, and now we have to multiply it with 1 divided by 4, and then I have CD, and then I have KL, I have CKL, and then I have CD, and this is multiplied with AC dagger, AD dagger, AL, AK, acting on phi 0 multiplied with E0 and multiplied with the amplitude, which is now T, K. No, sorry, I had a C there. That was wrong. This should actually be T. So I want to distinguish the amplitudes from the FCI, which are called for Cs, and those in copper cluster, which are called for Ts. And when we look at the contractions here, this is very much the same as we had before. So we are going to get 4 possibilities that will cancel the factor of 1/4. So let's just look at these contractions. So we are going to have an AI dagger, a J dagger, AB, AA, and then we have this AC in the operator for the 2-particle 2-hole excitations, AL and AK. So I'm only looking at the possible contractions, and we see now that the possibilities here are obviously the following. So this is a particle state, which has to match a particle state. And then we have this one, which has to match this one, like that. And then we can have all the additional cross terms, as before. So we can keep this arrangement, and then we can simply cross this one, so that this one goes over there. So that gives us one more term. And then I can take this one and contract that one with this one, and that one with that. So in total, I'm going to get 4 terms. This is the same as the interaction. So these terms, which I have Tij, AB, actually given by minus Tji, AB, which are also equal to T minus Tij, BA, which are also equal to plus Tji, BA. So we are assuming that these amplitudes obey the same symmetry relations as these anti-symmetrized interaction elements. So it means that I get 4 terms, and you can easily see that. And these terms, due to the definitions we've made with these anti-symmetrized amplitudes, are going to give us 4 equal terms. And that means that at the end, what I will get is E0 multiplied with this amplitude, which I should not insist on calling C, but T, of Ij, AB. That's the left, I always keep calling the right-hand side the left-hand side, it's the right-hand side. Okay, so then we have the next term, we want this to be equal to phi Ij of AB, and then I have my Hamiltonian of E of T2 multiplied with phi 0. And now I'm going to write this out in full glory. So what I'm going to get now is phi Ij AB, and the Hamiltonian is E0 ref, the reference energy, plus Fn plus V of n. And this is now multiplied with 1 plus T2 plus T2 squared plus, and then finally phi 0 here. So if we take the first term, then what we see then with the first term is that we are going to have a constant E0 ref multiplied with 1 and phi 0 and that one. So that has to become 0, right? So this one with that gives us 0, because we are trying to match a state which is a 0-particle 0-hole with a 2-particle 2-hole. The next term is more interesting. So if I still stay with E0, I have a T2. Now this T2 creates a 2-particle 2-hole state multiplied with a 2-particle 2-hole state. So this term here multiplied with this is going to give us something which looks like this, except that now we have E0 ref. So I can move that to the other side so that I get Tijab multiplied with the, so if I reshuffle a little bit, what I'm going to get now is the following. So let me just rewrite that. So I'm going to have a phi ij AB, and then I have this Fn plus Vn, the one body and the two body operators. And then I have 1 plus T2 plus 1/2 T2 squared, etc. of phi 0. And that is going to be equal to ECCD minus E0 ref multiplied with Tij AB. And that is the same as delta E CCD. It's an approximation to the true correlation energy multiplied with the amplitudes. Okay, so let's breathe a little bit here. Now, the terms which you see here, this term here is something we already calculated. So this term contains now, if we look back here, it contains this term here is now given in terms of the amplitudes. So you see now the nonlinearity, because this one is now given by 1 divided by 4. And then I'm going to change the indices. So I write CD, KL. There is an amplitude, T, KL, CD. And then there is an integral over KL of V, CD. So this is nonlinear in the unknowns Tij, AB. And these are unknown. Okay. So now comes the laborious and pretty boring part, because now we need to evaluate what we have here. So these equations, which we are going to go through now, we are going to derive them algebraically. But next week, you will see how we can derive these diagrammatically. And with a diagrammatical approach, it's much, much easier to see which terms have to be zero and which are non-zero. So the diagrammatic approach is very powerful, especially when you now have seen that even with this simple truncation, T2, you're going to get equations which are actually a little bit boring to go through, the derivation of, okay? So what we're going to simply do now is to look at these different terms, okay? So let's just break down the left-hand side of the equation. So the right-hand side is now set up. We have it here. We don't know these coefficients, so we need an algorithm for finding these coefficients, okay? So what we are going to get then is now the following. So we have phi ij AB, and then I'm having Fn, and plus V of n, multiply with 1 plus, and then we have T2 plus 1/2 T2 squared, etc., of phi 0. So let's start looking at the equations. So 1. And now let's see if I can trigger your intuition here so that you can actually set some terms to 0 without running any calculations. So if you look at this term, is this something which would be 0 or non-zero? So this is a yes, no. 0, not 0. Yeah. 0, exactly, because this guy here, when it acts here, produces at most a 1 particle, 1 hole state. But I have to match it with a 2 particle, 2 hole state. So this is 0. And now I cannot use my old joke any longer, because my old joke, which some of you may have heard, is that what is 0? That's the number of points Norway used to get when they tried to qualify for the World Cup. But this is no longer the case. So I have to find another way of defining 0, right? Previously, also, we had this Melody Grand Prix, where Norway's also always got 0 points. But that has also changed. I have to find a way to redefine 0. Anyway, so this term here has to be 0. So let's look at the next one and see if we can keep being relaxed and not doing any calculations. Yeah. It could be 0, but it can also be non-zero, actually, unfortunately, because the action here, this could actually remove a particle hole pair, but it could just create a new particle hole pair. So the action of Fn on this one could now just give us a new one, 2-particle, 2-hole state, which then could match this one. So actually, this term is something we need to look more closely at. So we can just leave this. So intuitively, you could have said that that could be the case, but we need to look a little bit closer at it. So let's take the next one, IJAB. Let me just look at my own cheat sheet here. Yeah, so let's, so we would then have an Fn of T2 squared. That has to be 0, because then we could actually create a 4-particle 4-hole state. And we cannot match that because this operator is a 1-particle 1-hole operator. So that one disappears. So that means that we can actually leave out all the higher order terms for this Fn. So Fn, I would also be tempted to say the second term, that this could be 0, but we need to investigate that. But at least the first ones and the third one here are going to be 0, and also all higher order ones. That's pretty obvious. If we now look at the next term, and when we have IJ, AB, and then we have the term V of n of phi 0. That's non-zero. So we just put non-zero here. And then we take the next one, which is phi ij AB. And then we have Vn of T2 of phi 0. Yeah, also non-zero. And then there's a tricky one because IJAB, and then we have Vn, and then we have T2 squared of phi 0. That non-zero, exactly. That's also non-zero. But then, if I take a T cubed times V of n, then I will be left with a 4-particle 4-hole state, which will not match the 2-particle 2-hole states. So the terms we need to look at are these different terms, this one, that one, no, sorry, this one, this one, this one, and that one. So let's take a look at these terms here. Right? And let's start with the term which deals with, so let me just find the term which now has the Fn operator. And that operator is given by PQ. And this is one which intuitively, I would also have said this has to be 0, but let's check that. So in principle, what I have then, when I look at this term, phi ij AB, so it's useful to check some of them. I would also, as you said, would have intuitively said, this could probably be 0, but let's check it. So what we have then is this specific state, which now acts with Fn, and then we multiply that with T2. So what that means is that we have a sum over PQ, but then we have also the operator, which is going to give us CD, and then we have an ALK. So we have this state, the two particle, two hole state, and then we have the operator, which is AP dagger, AQ, and this is then multiplied with AC, AD dagger, AL, AK, and this is then acting on phi 0, and it's multiplied with this unknown amplitude, KL, CD, and then we have the operator itself, which is P of F and Q, which has this integral here. So let's now just simply take this term only, and we look at the contractions. So let's just write out the contractions. So what we're going to have then is phi 0, and then we have AI, AJ, dagger, AB, AA, and then we have AP dagger, AQ, and then we have AC, AD, AL, acting on phi 0. So this term is a little bit deceiving, because you could have thought that we could actually get back with a one particle, one hole excitation, because we have the operator Fn. But let's look a little bit closer at the possible contractions which we have. So one possible contraction is that the hole states are not affected by the operator, okay? So that means that we let this one be contracted with that one, and this one with that one. So the hole states are not affected by the operator. Now, the operator is of a one body type. So I could now have this contraction, and I can have this contraction. But then my whole particle line here has to match the other bystanding particle line. So this is actually non-zero when we look at it. And diagrammatically, it's going to translate into something which looks like this. So let's set up the Kronecker deltas. So I have a delta I and with a delta K. I have a delta J with a delta L. And then I have one of the particles now, which is a bystander. So this one is not affected by this one body interaction, and it simply finds its mates here. So that one gives me a delta B of D. But then I have a delta A of P and a delta Q of C. So this is going to give me a term here. So there are no minuses when I look at the contractions. So this is going to give me a term now where, so you see that the I and J's, they are fixed, because this is something which I have fixed these subscripts and superscripts. The states where I'm running over is CDLK, that's the operator. But due to the Kronecker deltas, the only one which is not constrained by the outer legs here and here is actually the one which then includes this C, which has to be equal to Q here. So C here is then fixed, and the same with A. So that means that what I'm getting is a sum here, which looks like a follow. So I'm going to get a C here. There is a factor of, which I'm leaving out now, because what I did here was actually to leave out the factor 1 divided by 4. But there is, due to this one, there is a factor of 1. It should be a 1 divided by 4 as well. So if I look at this explicit contribution, which you see here, of this type, it's going to be 1 over 4. When I only take this term, this specific contraction into account, only that contraction. So then I get an element A here. I have the operator F, and I have C. And then what I'm getting is an amplitude which is equal to T, and K and L were fixed now to be equal to I and J. And A is also a term which was fixed to be equal to C. So C is here. And then I have B here. So B is here, like that. So that specific term now, when I look at the sum, I have 6 indices I'm summing over. Due to the Kronecker deltas, it reduces to sum of only one of them. So this term is actually non-zero. Now, what you will see if you do the contractions in addition here, so now I just kept these guys contracted like this way, but there's nothing which hinders me now to take this one and that one. So when I add up all the possibilities, the factor of 1 divided by 4 will disappear. So that was one possible contraction. But we have other ones. So because now you saw that I kept the whole lines fixed, they were not affected by the interaction here, which is of a one body type. I could now set up a similar term here in the contractions, which involves only the whole states. So if I now bring this back again, I have a new term, which is going to be AI, AJ, AB, AA, and then AP, AQ, and then I have my AC, dagger, AD, AL, and AK. Now I could say that, okay, I let the particle states be unaffected. So I could now run this contraction here. This is non-zero, and also this one. But then I would need to contract the whole states with the operator. So I could actually have this one, and that could contract with that one. And finally, this one has to join that one. Here again, I will get 4 more, and they will take into account the state. The factor 1 divided by 4. And if you look at this one, so what I have now, the interaction acts on this state L. So this one is going to give me a minus sign because I have a whole states which are being contracted. So that will give me a minus L, and there will be an L, and then I have an F, and I have a J, and then I have a T, I, L, A, B. You see the pattern here now? So I actually get 2 more terms when I do everything, 2 more. And this is where we stop today, because that was one of the terms. And tomorrow we're just going to set up the other ones. Everything which you see here is actually covered in the textbook by Shavit and Bartlett. They go through it in a very, in-depth way. They set up all the possible contractions, and they set up the equations for T2. And this is in chapter 9.3 of Shavit and Bartlett. So I'm just showing you basically what is in the textbook. So 2 more terms when we look at this one-body operator. So we're going to get another term, which is going to be a sum of K, and it's going to have a K, this F, and I, and then T, K, J, A, B. And finally, there's one term which has a plus sign, and that is the one where we have particle states. And this gives us a B of F of D, and then I'm going to have a T, I, J of AB. So I've reduced a sum over 6 subscripts into a sum over just one of them. So intuitively, we would have thought that they have a 2 particle 2 hole, and then a 1 particle 1 hole, and that could not match the 2 particle 2 hole, but it was a little bit subtler than what we thought. So this term gives us something which is non-zero. So now we have done, if we go back here, we have now done this term multiplied with this ones. And tomorrow we are going to set up this one multiplied with that. And then we have all the terms which will define the amplitudes here. I can see the excitement. Actually, these are things which you automatize. So when you've done it, you've gone through, it's always useful to go through the details and do it by hand. But this is something you would use a library like SymPy, which has a second quantization implementation, where you then can simply set up chains of operators, and that will find all the non-zero terms for you. And it will also spit out all the equations which you need to program. And you know that in SymPy, you can translate the equation into Python code, C code, or Fortran code. So these are things you would automatize. But it's useful actually to have done it. So I actually derived the equation T1, T2, and T3. I did it once many, many years ago. And it's, as I said, it's useful to do it once, but when you have more interactions and other terms you want to study, you don't gain a deeper insight by doing this again and again and again. But then the final equations, so I'm going to show you the algebraic derivation first, and then next week we are going to do it by diagrams. And when we do that, you will see that you can actually simplify the calculations a lot. And the diagrams you will get will be equivalent with the algebraic expressions which we got here. So at the end, we are going to move the left-hand side of this equation, which we have here. This is the, the right-hand side. I'm going to switch this over. So this is going to be equal to 0. And what this means is that you're finding a transformation of your Hamiltonian matrix. We are going to zero out some specific elements. So it's a similarity transformation. And then we have, if you move this one to the other side, put it equal to 0, you have an equation where you, by iteration, can find, by finding the root of the equation, then you can find these coefficients in an iterative way. And that's essentially how copper cluster theory is implemented. And with a pairing problem, life is much, much simpler, because in the pairing problem, these terms which you see here, they actually disappear. So that makes life much simpler.